Hello my friends, welcome to my channel Dr. Farhan Mumtaz. I hope this channel will be very effective for your learning and for your study improvement point of view. If you like my channel, please hit the subscribe button, like and share my videos with your friend and family and with your scientific community. Today my topic is to reproduce a D-shaped optical fiber surface plasmon resonance refractive index sensor based on Ag alpha Fe2O3 grating. This video is totally based on the COMSOL simulation. So in the simulation part, we'll try to reproduce this structure that is shown in your screen. Okay, like this. I enlarge it. So basically we have a D-shaped fiber, have a core with gratings. So let's start. I will show you the geometry of the structure. This is our D-shaped fiber, and we have this grating structures 1 2 3 4 5 6 7. So in this paper they have taken the number of gratings indifferently. We are going to reproduce this kind of structure, uh, spectrum of proposed SPR fiber sensor at external RI of 1.39, where we try to reproduce this electric field of Ag alpha Fe2O3 grating SPR sensor. So let's start. So first of all, we need to define the number of parameters that involving to define the geometry of D-shaped fiber SPR. So this one is our radius of the core. This one is radius of cladding. Silver grating thickness. Okay, so this one is our femitite grating layer of thickness. Okay, this one is the width of our grating. And this one is the separation of the grating, so we take it as a pitch. So I think we don't need it, this one, and don't need this one also. Okay, this one is our operating wavelength. And this one is our operating frequency. This one is Selmayr equation for core refractive index for clad Ri refractive index, and this one is for clad refractive index, sorry, core refractive index. Okay guys, this one I used to define the Selmayr equation for clad refractive index, that I can show you. So here is the Selmayr coefficient for fiber core and cladding. So here is our cladding refractive index coefficients. So A1, A2, A3, B1, B2, B3. Similarly for the core. So here we define for the clad, and here we define for the core part. So our clad is purely silica, and our core is purely not pure, it is a Ge doped germanium doped silica. So let's go toward our geometry. Geometry we taken as a unit length micrometer. Then we go to define our core radius. Okay, our core radius is here, we already define it. So this is our core radius. In parameter we have already defined our the parameters for the radius. Similarly we take it the cladding part, so build it like this. So we got a structure of optical fiber. So but our proposed structure is a D-shaped fiber. So D-shaped fiber is look like this one. So we are going to build a D-shaped fiber. So we need to define a rectangle of width 125. We need to define a rectangle with a width of 125, 60 height, and this is our location of a rectangle, that where we take it coordinates 0 and we took it as the center point. So build a rectangle, and now from okay guys, we need only this part to draw our D-shaped fiber. So we need a Boolean function partition here. So we took a difference here. Okay, we select a difference. We need a difference of this one and this one. So we got select an object here, subtracting this part, so we build. Okay, this is our D-shaped fiber geometry. We have defined it. Okay, let's move on. Okay, this is we use our external medium, or we can say surrounding environment. So this is our radius, we took it plus 10 or 20 whatever. Okay, so we have this our surrounding environment. Now we need to define the gratings structure like this one, two, some. Okay, we need to define our grating. I have already defined it here. This is the width of my grating, this is height, and we have a location where we need to build it. So I build this one. So it is already built, but you cannot see because it is quite smaller in size. You can see it here. Okay, this is my grating structure. So okay, we have defined our grating location here. So basically we need to define the number of gratings. So once we refer from the paper, we see it, the number of gratings they have defined in the paper in the different number. So different thickness of the fematite, he has taken 0, 3, 5, 8, 10, 12 and 14. So he got the maximum sensitivity of 12. So we have already taken it 12 for fematite. I can show you here 12. and this is for silver thickness that he is considered 45. So most of the cases he took it 40, 45, 50, 55, 60 and 65. Okay, that's all. Okay, now I need to make an array function to present the number of gratings. So array, you can get it here. Once you select it here, now you go for the linear, and then this is the offset of offset function of the grating. So once I would enable it, I got this sort of results. So this one is our one, and the remaining 9 structures of similar pattern is build it here. 1 2 3 4 5 6 7 8 and 9. So I need total number of 20 gratings structure. So I need one more array. So I took it 11 here and here with the displacement. Similarly, I use an array function from the transform tab. Okay, this is my 20 number of gratings that is defined. You can see that is in your clear from your screen. Now our geometry is defined in 2D domain. Okay, this circle we don't need it. I delete this one, build all. So it's our perfect geometry. So now it's time to define the material. So I need a cladding part of silica. So I select this one is our this one is our core. This one is silver grating because it is not shown because it's a quite smaller ring. So I just enlarge this one so you can okay, this one and this one all selection for material of silver gratings. So similarly for fematite, the top layer is selected. You can see. Now it's a time to define our refractive index external medium. So our external medium is this is I just took a boundary for later on to define the impedance condition. So I remove it. Okay, this one is I just took it as a Ri for impedance boundary condition, and here is our external Ri. So this one is our external Ri and this one is our silica. Okay, now going for the physics part. So here I already defined the impedance boundary condition. So how you get it? You can right click it here and select the impedance boundary condition from this tab. You got it, and you need to define where you want your allocate the boundary of impedance. So it is already allocated from outer boundary. Now it's a time to define the mesh. Okay, so I took already the number of sizes of mesh element that extremely fine for the code, and this is our remaining geometry that is taken as a curse. Maybe you took it as a normal for the remaining geometry. Normal or fine, it's up to you, whatever you want. Okay, this is meshing part we have defined, and now it's a time to go for mod analysis. So I am looking for mod analysis frequency, this one f naught, that I have already defined it in my parameters. My frequency is 2.99 hertz, approximately 3 hertz. After defining the mod analysis, I just need to find the effective mod index. So I am gonna to compute this. Okay, this will take some time. Wait for a while to see the results. In parallel, you can see the convergence plot. The iterations are converging at the limit of iteration errors. You can also see the progress of computation from this window, progress tab. Okay, the solution is near to ending for the computation. Okay, we got the number of mods here. Okay, I can enlarge to show you the situation. Okay, so it's quite similar to the model field that is shown in this paper. Okay, you can see this one is reproduced here with a quite good function. I hope you can understand the mechanism of the paper, that based on simulation how to reproduce for your understanding point of view. So now I'm going to reproduce this plot, the curve of the transmission coefficient. So let's go to 2D plot. So this is exactly look like the plot. This is a dip of transmission. So how you can plot it? You just need to define the parameters that involving the transmission coefficient. So I can show you the equation of the transmission coefficient that he have used to draw the plot of transmission coefficient interference dip. Okay, this one. So this is quite similar to the curve line that is plotted here. The function you need to go drive, and here you need to define the global evolution from here. And once you define, okay, I just use the number of parameter that is used in my parametric sweep function: 13, 14, 15, 16, 18, 19 and 20, the refractive index that I have evaluated this one. So here I define the expression that is used to define the transmission coefficient here. T equals to exp of minus 4 pi by lambda imaginary refractive index multiply length. Length is taken is 10 millimeter in this paper. We can go to the introduction part, the abstract part. We can see the amethyte coated silver grating significantly enhanced the sensor as revealed by the simulation outcome. In this work, maximum response S of the sensor can reach 6.5 micrometer per RIU. It is quite high when the external RI was 1.33 to 1.39. As I have taken this curve is on 1.39 refractive index, the surrounding refractive index, with a 45 nanometer thick silver grating. So I already defined in our geometry 45 nanometers thick silver grating, 50 nanometer width air gap and 12 nanometer thick amethyte alpha Fe2O3 that is used in our simulation. So here is the plot. So this plot is quite similar to the plot produced in this paper. We have successfully reproduced this plot in our simulation result. I hope this all work is very helpful for you in respect of guidance and in the respect of your research. If you like my working on the simulation of COMSOL, you may like my channel, subscribe my channel, share my channel to your friends and acquaintances so that my channel will be grow and I can make more useful videos for you. Wish you very best of luck. Wait for the next lesson. Thank you very much.